In this tutorial, we're going to design the supply water system for residential zone. The terrain area is 30,000 square meters, where it's projected to build 12 buildings. 10 buildings are for residential use and 2 are for commercial use. The residential buildings named A, B, C, D, F, G, H, and I are buildings of 10 stories and 42 apartments each. The buildings named E and J are buildings of 5 stories and 22 apartments each. And the buildings named K and L are commercial buildings of an effective construction area of 780 square meters and 130 square meters respectively. The measured pressure at the connection point to the main supply water system that comes from the street is 360 kilopascal. The first things to do is calculate the daily average water demand ADD required by the system. It's important to mention that each state has its own values to calculate the average daily demand, but a good rule of thumb for a residential project is estimate this average between 250 and 300 liters per day per person, and for commercial buildings 20 liters per day per square meter. The average daily demand can be calculated with this equation, where W is the estimated water demand by one person in a day. P is the media of the person that live in the apartment, normally taken as 4 persons. And A is the quantity of apartments that compose the building. In example, for the building A, the average daily demand is 50,400 liters per day. The next step is calculate the maximum daily water demand, which is considered as 1.6 times the average daily demand, giving a result of 80,640 liters per day. Now, we calculate the peak hour water demand, which is considered as 2.5 times the average of the daily demand, giving a result of 126,000 liters per day. Finally, we compute the needed fire flow, which is calculated in accordance with the American Water Works Association M31 standard. First, we need to calculate the construction factor CI with the equation 1n-2, where F is a coefficient related to the class of the construction, which value is 1 for the joisted masonry in accordance with the table 1n-2 of the American Water Works Association M31 standard, and A is the effective area plus a 50% of all other floors for class 1 to 4. The area of the building A is 1,476 square feet plus 50% of 9 stories, giving a result of 2,937.96 gallons per minute, which is rounded to the nearest 250 gallons per minute. Now, we can calculate the needed fire flow NFF with the equation 1n-4 of the American Water Works Association M31 standard, where OI is the occupancy factor equal to 0.85 for limited combustible buildings, in accordance with the table 1n-3. XI is the exposure factor equal to 0.15 for the building A, in accordance with the table 1n-4, and PI is the communication factor, which is equal to 0 because the building hasn't passed away, giving a result of 2,932.5 gallons per minute, which is rounded to the nearest 500 gallons per minute. The final value of the NFF is 3,000 gallons per minute, which is 68,137.41 liters per day. With the basic flows calculated, we proceed to determine the design flow of the system based on the peak hourly demand and the maximum daily demand plus the fire flow demand, whichever is greater, in accordance with the American Water Works Association M31 standard. In this table are the final results, and we can observe that the design flow is the maximum daily demand plus the needed fire flow. Defined the design flow, we proceed to trace a proposal line to distribute the flow, taking into consideration these recommendations. The pipes shall be placed at the right of way alongside of the road and is desirable to place them under the pavement just when it has to cross a roadway like an intersection. Less connection, less leaking problems. The valves shall be placed so that a pipe break will affect water service only in the immediate area of the break. A hydrant shall be placed at the dead end of the line, in the highest point of the system, and in an intersection. With all these recommendations, we proceed to draw the proposed main supply water system pipeline, as is shown in this figure. Now we proceed to divide the system in sections and distribute the design flow for each section according with the flow direction, as is shown in this figure. After that, we define each node of the system, its elevation and distance between them, as is shown in this figure. Now we are ready to select the pipe material, calculate the diameter required by the system, its velocity and losses for the pipeline. It's a good practice to make the design with 3 different types of diameters and materials to select the best option in terms of performance cost for the system. In this tutorial, the system just will be designed for steel material, according with the American Water Works Association M11 standard. First, we are going to calculate the diameter required and losses generated by the diameter chosen. The diameter is selected by iterating process according to the losses, with a good judgment trying to select a diameter that generates adequate losses for a good performance cost criteria, taking consideration the minimum diameter allowed by the American Water Works Association M31 standard, which is 6 inches. These losses are calculated with equation 3-2 of the American Water Works Association M11 standard, transformed to MKS system, because it's more simple to work in metric units to calculate the final pressure in the system, where HL is the loss, L is the length of the section analyzed, Q is the flow rate, C is the Hansen-Williams roughness coefficient, which is 140 for brand new steel pipes, according with the American Water Works Association M11 standard, and D is the diameter of the pipe. In example, for the section A6, the equivalent loss length is 1.01 meters. In this table are the diameters required by the system and the losses generated by the diameters. With the diameter of the system calculated, we proceed to calculate the minor losses due to the connections, as elbows, tees, or valves, and create a more detailed analysis of the distribution system by dividing the network in the smallest section. These minor losses are calculated with equation 3-15 of the American Water Works Association M11 standard, where K is the resistance coefficient obtained from the figure 3-5 of the American Water Works Association M11 standard. P is the mean velocity in the accessory, calculated with equation 3-5, and G is the force of gravity. In example, for a sudden contraction from 6 inches to 3 inches in the section 2-3, the mean velocity is 3.784 meters per second, and K is equal to 0.32, according with the table 3-5. The head loss is 0.234 meters. In this table are the values of the resistance coefficient for the accessories used in the design, according with the material and diameter of the pipe that compose the distribution system. The final step of the design is calculate the pressure available at all points of the distribution system, that should be at least 140 kPa at the ground level, according with the American Water Works Association M31 standard. This distribution system is designed to carry the water into the tanks of each building at the ground level, and not to supply the demand of each story of the building. That pressure shall be supplied by the hydropneumatic system of each building. The pressure at any point of the distribution system is calculated with this equation, where P1 is the pressure in the first point of the section analyzed, in meters of water columns. Delta H is the differential elevation between the 2 points analyzed, and HL summation is the losses of the section analyzed. In example, for the section A-1, the pressure at the point 1 is 327.87 kilopascal. In this table are the pressure available at any point of the distribution system. In this figure, we can observe graphically the pressure distribution in the system. In the highest point, the residual pressure is 143.17 kilopascal, and in the lowest point, the residual pressure is 180.17 kilopascal, which complies with the requirement of the American Water Works Association M31 standard. With this, conclude this tutorial.